Now, before I start doing this experiment due to a Danish physicist by the name of Ørsted, let me preface it by saying that when I'm running an electric current through this wire, it's going to be a rather large electric current, and this is not something that you should be attempting to replicate yourself. If you don't know what you're doing, this is the sort of thing that can cause a fire. So don't do it. Anyway, when Ørsted did his experiment, one way you can do it is you can lay a wire right over a compass needle, like so. And when I go ahead and cause a current to flow from the left of the screen to the right of the screen, we see that the compass needle swings out. We can do the exact same thing, but with the compass wire going under the compass needle, and we see the compass needle swings the other way. Also, if we were to reverse the direction of the current, we would get the reverse results.
So what are we supposed to make of Ørsted's experiment here? Well, since we have a current flowing and we see that it caused a compass needle to deflect, we can conclude that moving electric charges can create a magnetic field. Now, we've seen previously that stationary electric charges do not do that, but moving ones do. Now, let's try to get a sense for how these magnetic fields work. So let's go ahead and we'll draw a current flowing from left to right. And in this case here, if we were to play around with our compass needle a bit more, what we would see is that the magnetic field lines that we create are circles. And they run, the plane of the circle is perpendicular to the magnetic field. So, sorry, I'm doing a bad job of drawing in 3D here. The plane of the circle is perpendicular to the magnetic field, and we can see that the circles loop around on themselves. They don't start or stop anywhere. The only reason I've got this little break here is just to show that the line is going behind the wire. We'll draw in a few more just to help make that maybe a little clearer. Okay, so something like that. And we'll go ahead and note our magnetic field here. The symbol for magnetic field is B. Now you might wonder why the heck B? Well, it turns out that the person who put the theory of electricity and magnetism into a solid mathematical basis was a Scottish physicist by the name of James Clerk Maxwell. And for reasons known only to him, he worked through the variables that he needed purely in alphabetical order. The first thing he needed, he called A. The second thing, the magnetic field, he called B. And so forth. He just worked his way down the alphabet, and so the magnetic field is B because it was the second thing that Maxwell was thinking about. Anyway, a way to help remember, you'll notice that these have a direction. Remember, compass needles like to orient with the local magnetic field. The way to remember how this orientation works is you take your right hand and you place the thumb of your right hand so that it's pointing in the direction of the conventional current. So go ahead and try that right now. So the thumb, take your right hand, point the thumb to the right. And what you'll see is that the curl, the way your fingers of your right hand curl, is how these magnetic field lines will go. So the magnetic field lines will follow the curl of the fingers of the right hand if the thumb is placed in the direction of the conventional current. To help maybe visualize this a little better so that I can clearly show that these magnetic field lines are perpendicular to the current, let's take a look at a case where the current is coming out of the page. So remember, if we have something coming straight in or straight out of the page, like a current, we'll draw it as a circle with a dot, and that is the point of the arrow flying at you. So go ahead and try to figure out the sense of the magnetic field lines using our right hand rule here. Now there's going to be multiple right hand rules, so I like to call this one the hitchhiker rule. So go ahead, use the hitchhiker rule to figure out how our magnetic field lines are going to orient. Yeah, so they're going to orient counterclockwise. So the magnetic field strength will be stronger near the wire and weaker as we get away from the wire. So I'm indicating that by a higher density of magnetic field lines here, a lower density of magnetic field lines as we get further away. And we will have magnetic field vectors as well. And we read these magnetic field line diagrams the same way that we did with electric fields. So say if I want to know the magnetic field vector at this location right here, I would imagine the line that would pass through it and draw a vector that goes tangent to it. So here the magnetic field strength would be, pretty reasonable, pointing off tangent to what would be a counterclockwise circle that would pass through here. Now say if I wanted to know it here, it'd be the same game, but since the magnetic field line density is higher here, I would draw a longer magnetic field vector there. Okay, and let's think about, so that's if we were looking at the wire from this direction. What if we were looking at it from this direction? Well, in that case, our current would be going into the page. So go ahead, pause the video for a moment and draw the magnetic field map that you would have for a current going into the page, and then I'll get back with you. All right, so you should be getting that your magnetic field map looks the same, except that your circles, so closer spaced closer to the wire, further spaced as you get away from the wire, except now the lines should be oriented clockwise. If you take the thumb of your right hand, point it into the screen, you'll see that the fingers of your right hand will curl clockwise. Now, this is probably a good a moment as any for me to give you a cautionary tale here. As you start, especially on a test or something like that, as you're trying to visualize magnetic fields, you'll be using these right-hand rules a lot. And a danger that you can run into is if your dominant hand is your right hand, you can find yourself holding your writing implement, and then suddenly you use your left hand to find the magnetic field because you're holding onto the right hand. Now you're supposed to use your right hand. Now if you take a look at, say, if you point the thumbs of your right and left hand both toward you, you'll see that the fingers of your right hand will curl counterclockwise, and the fingers of your left hand will curl clockwise. So in other words, if you use the left hand, you'll get exactly the wrong answer. So my general rule is whenever you begin to think that you might have to use any kind of a right-hand rule to be thinking about magnetism, the instant you start to think about that, I kid you not, if you are right-handed, sit on your left hand. That will force you to put your writing implement down and use your right hand to do your visualizations with the magnetic fields and forces. Conversely, if you write with your left hand, then firmly grasp your writing implement so that you don't feel any temptation to use your left hand. All right, so since it's really hard to draw this stuff in 3D, and a lot of times you will want to think about what if the wire is going to the right, let me show you what physicists usually do to try to visualize this. The usual convention that we'll do is we will just draw in pure cross-section. So here's my wire going to the right. Now, instead of attempting to actually draw the magnetic field lines going in and out of the page, magnetic field lines going around circles, we'll instead just look flat out in cross-section. So you'll draw a bunch of dots because when you have field lines, you have lots of them. Yeah, that'll do for now. And they should be closer spaced near the wire and further spaced away from the wire, like so. You guys are getting weaker. Now on the other side of the wire, we'll draw a bunch of X's. Now, you may hear some physicists, instead of calling them X's, call them crosses. And that's because cross is British for an X shape, just like naught is British for 0. So the game of tic-tac-toe is, in the UK, is actually called noughts and crosses after the shapes. Anyway, we're drawing in pure cross-section here. So the idea is, let's say I pick these two field lines right here, or say that pick this point right here. What I'm looking at right here is this is a magnetic field line coming out of the page. It will match with that X over there because that's where it's coming into the page. So these are actually part of the same line. And so you'll visualize this and say, okay, it's coming out of the screen up here, and then it'll start, as it gets in front of the screen, it'll be heading down and loop back, and it'll punch through the screen, going into the screen here. Then behind the screen, it'll loop back and come up like so. So in my bad 3D drawing here, this bit right here where it punctures out of the plane that the wire is in, that became the dot I drew. And this bit here where it punctures into the plane of the cross section I drew, that will be the X that I drew. So that is usually how physicists will draw this. It's a very standard thing where we draw things in cross section and then the viewer is expected to complete the 3D visualization in their head. All right, so with that, let's start to quantify things. Now, we'll eventually tie the fields into forces in a later video, but for now, I'll just go ahead and introduce the magnetic field and say, for a long straight wire, the magnetic field strength is equal to mu naught I over 2 pi r, where r is the distance you are away from the wire. And I is the current. So I can dimension this in. This would be that distance r right there, if I was interested in this point right here. Now the unit of magnetic field strength is the Tesla. We'll do a better definition of it later. But for now, this quantity mu naught, it gets a really weird name. It's called the magnetic permeability of free space. That is a name that doesn't mean anything. And before the redefinition of SI units, it was exactly equal to 4 pi times 10 to the negative 7 Tesla meters per amp. This is now no longer exact. The details of this get annoying, but suffice it to say that when developing the theory of electricity and magnetism, you're free to choose the values of epsilon naught for electricity and mu naught for magnetism, both the numbers and the units, believe it or not, as long as the product of epsilon naught and mu naught is 1 over the square of the speed of light. I'm not going to get into how that works, but suffice it to say that there's some freedom to do that. Now, it turns out that when dealing with magnetism, there are lots of factors of 2 and 4, and there are factors of pi showing up all over the place. And so the value of mu naught was chosen literally to give you a pi to cancel up against, just to make doing the math easier. But with the new SI, the values of epsilon naught and mu naught are no longer exact because the speed of light itself has been made exact. So it's still true that the product of epsilon naught mu naught has to be 1 over the speed of light squared, but in the new SI, the value is no longer exactly 4 pi times 10 to the negative 7 Tesla meters per amp, but it is very close to this. But it's now an experimental value. It's no longer exact. Now, to give some intuition for how big the Tesla, our unit of magnetic field strength, is, this is kind of like the farad was for capacitance, where it tends to measure pretty big values. So the magnetic field strength of the Earth depends exactly where you are, but if you're somewhere along the surface of the Earth, it's around 50 microteslas. A MRI machine, on the other hand, which that is getting to be pretty big. If you've ever had to take an MRI, you know they make you take all the metal off of yourself, and the thing just sits in itself in a giant room, and you can see that there's a lot of power going into it. Typical MRI machine, somewhere between 2 to 7 Teslas. And pretty much the biggest thing ever made is a laboratory superconducting magnet that was on the order of 20 Teslas. So more often than not, unless you're dealing with problems that have to do with MRI machines or something like that, you're probably going to be working in the tens to hundreds of microteslas, maybe a millitesla, something like that. That's what's going to usually be typical, but it could get up as high as about 20. All right, so let's go ahead and try making this a little more concrete here. Let's say I have a wire carrying 10 amps to the right. I have another wire carrying 10 amps to the left. So I'll, for the moment, call that I1 and I2. But I'll note that since they're equal, we'll eventually call them both I. I just want to distinguish them for the moment. Let's go ahead and say that these wires are 4 centimeters apart. And I am interested in the magnitude and the direction of the magnetic field at this location 2 centimeters above the upper wire. So how would we go about doing that? Well, the thing is that we're going to actually have to consider 2 sources of magnetic fields. And it turns out that magnetism also obeys superposition. So our strategy is we'll find the magnetic field strength from wire number 1 and from wire number 2 and add them as vectors. So let's get the directions out of the way first. So at this location right here, I would like you to try to figure out the direction that the magnetic field will point purely from wire number 1, disregarding wire number 2 for the moment. Okay, so you should be getting that at this location here, the magnetic field due to wire number 1 will point out of the screen. And remember, you get that by pointing your right thumb to the right in this case, because the current of the upper wire is going to the right. And you know that the magnetic field lines are running in circles, and you can see that your fingers above your thumb are coming out of the screen. So at this location right here, the magnetic field due to the upper wire is coming out of the screen. Okay, now go ahead and repeat this for wire number 2, the lower wire. Okay, for that one you should be getting that it's going into the screen. And again, it's the same deal. You put your thumb along the wire, and you can see that that above the wire, the fingers of your right hand are curling into the screen, above the screen. So the magnetic field will be pointing into the screen there. So that means to get the so now we can already work out, since the currents are the same and wire number 1 is closer, we can already work out that the magnitude of the contribution from wire 1 at this location will be greater than wire 2. So that means that we know that the overall magnetic field has to point out. So we've worked out that the overall magnetic field is pointing out, and to get the magnitude of it, we'll have to subtract B1 and B2. Okay, so that's going to be mu naught I1 over 2 pi r. This will be mu naught I2 over 2 pi r. Now, since I1 and I2 are both equal to I can rearrange the surrounding, R1, R2. I can get that this, where R1 is this distance here, and R2, we're measuring from this wire here, is that distance there. So R1 will be 2 centimeters, R2 will be 6 centimeters. All right, so now going back here, this will be mu naught. Since I1 and I2 are both just I can group them together, over 2 pi, 1 over R1 minus 1 over R2. And so let's go ahead and substitute in. Now, you can look up, if you Google mu naught, it'll give you a number to put in. I would recommend not doing that. I would leave it as 4 pi times 10 to the negative 7 Tesla meters per amp. And that's because we're dividing by 2 pi here. So see, that cancels and gives you a 2. Makes things a lot cleaner. Okay, our current is 10 amps. And since this has meters in it, we've got to get these centimeters into meters. So that's going to be 1 over 0.02 meters minus 1 over 0.06 meters. So that's going to give you 6.67 times 10 to the negative 5 Teslas. And sure enough, that's going to work out to be 66.7 microteslas, a little stronger than what the Earth generates near the surface of the Earth. So that seems like a perfectly reasonable value. Now notice, of course, we were working at cross purposes here, but these are 10 amp currents. So to get noticeable magnetic fields, you generally have to run some pretty stout currents, or you have to be really close to the wire. Okay. Now, let's look at some other shapes. So let's say instead of having a long straight wire like we were just dealing with, you have a loop of wire. So we'll go ahead and say that it's carrying current I like so. Actually be a little easier if I make it go counterclockwise. Sorry, if I make it go clockwise. So let's say I have I like so. To get the direction of the magnetic field, we can still play the same game. We can use the thumb of our right hand. And what you'll see is if you place, say, the thumb of your right hand here, in this region here, your fingers will curl into the loop. Something like that. And outside the wire, they'll curl out of the loop, like so. Okay. If I try to draw this edge on, sorry, it's going to look ugly, but I'm just going to try. If I try drawing this edge on, the magnetic field lines are going to kind of do one of these things. Something like that. All right. So anyway, to get our values for this, let's say this is radius r. At the exact center of the wire, and only for the exact center of the wire, or center of the loop, it'll turn out that the magnetic field at the center of the loop is mu naught I over 2 times the radius, no pi. And keep in mind, this is only for the center of the loop. Still, though, it's a reasonably convenient thing. And you can go ahead and imagine what would happen if you stack a whole bunch of loops of wire together. If you do that, you create a thing called a solenoid. Now, let me try to do a better job of drawing one of those. Not that it's going to go that well. Whoops. So it's a thing called a solenoid. And it's just basically you take a wire and you wind it around a lot. So we'll say that you've wound it n times. So we'll say you have n turns of wire. And you did that winding over some length L, like that. It turns out that, except right at the very edges of the solenoid, the magnetic field strength in the interior of our long solenoid is pretty much mu naught I n over L inside. And although the magnetic field strength is low outside, ideally it's 0. In reality, it's very small. And again, the magnetic field lines will be pretty much just uniform within the solenoid like that. And then they loop way out over here, very, very far apart. So in here, whoops, in here, this is where B is pretty much almost everywhere inside the solenoid. mu naught I n over L. And then out here, it's very weak. And so you can usually get away with approximating it out to 0. All right. Let's just do one more example here. So let's say I have a wire I put one loop into like that. And this loop is in the same plane as the wire. We'll go ahead and say that the diameter of my loop is 2 centimeters. So that's going to make the radius of my loop 1 centimeter. Now let's go and figure out if we are carrying a 5 amp current like so, what is the strength and the direction of the magnetic field at the center of the loop? Now, the strategy for something like this is you're actually going to have to think of this as a long straight wire plus the loop like that. So this loop is carrying 5 amps. This wire is also carrying 5 amps. This is the equivalent problem. In practice, you got it by looping around like that, but when thinking about it magnetically, this is the way to divvy it up. So this distance here is going to be little r is 0.01 meters. And if I want to know at the center here, this is going to be big R is also 0.01 meters. So that makes it a little more convenient. Now for both of these, you should be able to use the hitchhiker rule and convince yourself that at the center here, that the magnetic field points in. And we want to know what that strength is. So the strategy here is going to be, say, this is going to be, that the total magnetic field will be the magnetic field due to the long straight wire part of it, plus the loop. So this will be, for the wire, that's mu naught I over 2 pi little r, where r is the distance from this wire. This is going, for the loop part, there'll be mu naught I over 2, pi, big R, where R is this radius. Okay. So, but in this case, little r equals big R. So I can rewrite this as B is mu naught I over 2. And just say little r, doesn't matter which one I pick. And I'll be left with 1 over pi left over from here. And here there is nothing left over, just plus 1. Now, when we get to substituting in our numbers here, we're going to have 4 pi times 10 to the negative 7 Tesla meters per amp. This will be over 2. My radius is 0.01 meters. Now, before we go too crazy here, I would urge you to not just immediately punch into the calculator for once. It'll be a little nicer if we can clean up the pi's just a little bit, and you totally can. So here I can cancel that out. Oops, missed my 5 amps there. So this will be 2 times 5 is 10 pi times 10 to the negative 7 Tesla meters, because I already times by my 5 amps. And then if I divide by 0.01 meters, that is going to increase this by 2, so that becomes 10 to the negative 5 Tesla, just Teslas now. So I've multiplied this, and divided by that. But I kept the pi while I did it. So the reason, so I have 1 over pi plus 1. The idea is I can treat the pi like it's an algebraic variable. So this is going to be, let's see, we'll worry about the pi in a second. 10 times 10 to the negative 5 is 10 to the negative 4 Teslas. And now pi times 1 over pi is pi, and 1 times pi, is 1, and 1 times pi is pi. There we go. And so this is going to work out to be, let's see, 3.14, 4.14. 4.14 times 10 to the negative 4 Teslas, or 414 microteslas, which is still a reasonable-ish number, about 8 times the magnetic field strength of the Earth. Reasonably strong current, and you're right in the middle of a tiny little loop of wire, so that makes some sense. Alrighty, so I'll just conclude with this little thought here. Going back to Ørsted's experiment, remember the idea was when I put a compass needle on top of this wire, we saw that the needle felt a torque. In order to have a torque, there must have been forces. So although stationary electric charges don't exert a magnetic force on things, moving ones do. So if moving charges can exert a force on our compass needle, it must also be the case that our permanent magnet compass needle can exert forces on the moving charges by Newton's third law of motion. This is indeed the case, and we will work on quantifying those forces in upcoming videos. So catch you over there.